Gibbs free energy is telling you the total chemical content. The work function is telling you the mechanical content. If you go back, the entropy is kind of telling you the thermal content of the system. Okay, well now, to kind of illustrate some of this and to get some material science into it, let's actually talk about the thermodynamics of simple solids. Now, in order to talk about the thermodynamics of simple solids, I'm going to have to get you into something that is a concept that is not always that easy to see, and that is the concept of lattice vibrations in crystals or phonons. I'm going to show you some math. You will never be tested on that math. I'm showing you solely for the purpose of you getting some way to understand what's being talked about. I hope you kind of grasp it qualitatively. I will not insist that you grasp it quantitatively or use it quantitatively. I just want you to understand what lattice vibrations are, because we need them later in the course, things like optical properties and so on, and how they pertain to the specific heats of solids. Well, let's first of all, if we're talking about a solid, unless we have enormous pressure, the PV term for a solid is irrelevant. It just doesn't matter. So we had two different variables. We had the Gibbs free energy when we control the pressure, the Helmholtz free energy when we control the volume. When you're talking about a solid, unless the pressure is enormous, you can forget the distinction between them. They are the same. The Helmholtz free energy is in fact much easier to work with. If you have been introduced in any way to statistical mechanics, or if you study it later on, you'll discover that one of the easiest things to calculate from first principles, from what they call the canonical partition function, is the Helmholtz free energy. Even in things like quantum mechanics, it's rather easy to use volume as a variable, because all of your quantum states are easily calculated for a given volume. In computational thermodynamics, it's rather difficult to use pressure as a variable, because every time you change the pressure, you change the walls, and that changes all the quantum states. It's really difficult to handle. So the Helmholtz free energy is much easier to work with, and it turns out to be convenient to work with, since the Gibbs free energy and the Helmholtz free energy, unless we have an enormous pressure, are effectively the same. So let's look at the Helmholtz free energy, E minus Ts. The energy of a solid, a function of volume and temperature, can be written as a summation of two terms. There is a 0-point energy, and this, by the way, we would calculate it from first principles. If you're going to do first principles calculations, you'll crank and grind a computer and get these numbers. You would first of all take all your atoms, and you would find the equilibrium crystal structure at 0 temperature, and you would calculate the cohesive energy associated with that. And that gives you some easier, your ground state energy, which is a function of volume. With modern techniques, that's quite easy to I shouldn't say quite easy. It's very straightforward to calculate. People do it all the time. Any graduate student trained in computational material science will be able to do that calculation from first principles and get a pretty good answer. That p0, of course, is a function of volume only. It doesn't depend on the temperature, because the temperature is 0 when you calculate. The thing that's harder to calculate, somewhat easier to measure, is the thermal contribution to the energy, how this energy changes as you bring the temperature up. Well, I can write that as the integral from 0 to t of the specific heat at constant volume dt, where the specific heat at constant volume is the change in energy with respect to temperature at constant volume. And this would be related to actually the second derivative of the fundamental equation. So I can, if I know the specific heat as a function of temperature, I can calculate the energy as a function of temperature and volume. The entropy, I would need to take the connection between entropy and heat, and say that the entropy is the entropy at temperature 0, which is equal to 0 by the third law if we're talking about the equilibrium state, plus the integral from 0 to t of dqv over t prime, where this is the heat that is added to increment the temperature divided by the temperature. Well, the heat that's added to increment the temperature is just cv dt. So the entropy as a function of volume and temperature is just the integral from 0 to our current temperature, the specific heat at constant volume divided by the temperature dt. The thing that you immediately notice here is that if we want to know the Helmholtz free energy of a crystalline solid, we only have to know two things. The energy at absolute 0, which you could calculate if you want to or measure, and the specific heat as a function of temperature. So it becomes very important to understanding the thermodynamics of a simple solid to focus in on the specific heat, what it is and how it varies with the temperature. It turns out, yeah, question?
So you might decide, so entropy is equal to 0, it has 1 microstate, which means per crystal.
Perfect crystal.
Why in quantum mechanics do they say the ground state is all vibrations?
That's a 0-point vibration. It doesn't add entropy. There's no entropy associated with a 0-point vibration. That's at n plus 1/2 h nu, yeah. No, because it's a single state. It's a fixed state. A fixed state has no entropy. The 0-point vibrations are fixed states, so they have no entropy. The entropy comes from the fact that you can get a distribution of vibrational states. That's where the entropy comes from. If there's only one vibrational state, there's no distribution, and therefore no entropy. The ground point vibration is actually an enormous subtle thing. It comes originally out of the Dirac version of quantum mechanics, and it's like electron spin. It's a mathematical result that is not that easy to explain in anything other than that's what you get when you plow through this. Well, it is an actual vibration. It contributes to the vibrational entropy, but it's something that comes in mathematically. It's not something that you can do anything about. You can't do anything about it. Nature can't do anything about it. Therefore, it doesn't contribute to the entropy. All 0-point vibrations at the same time. There's nothing to vary about it. Therefore, there's no entropy. But things like the 0-point vibration and half-integral spin are things that it doesn't make an awful lot of sense to spend a great deal of time thinking about, because they're very subtle concepts. Okay? And they actually come more from the mathematics than from the physics of the problem. Well, I should take that back. They're a mathematical consequence of the physics of the problem, which is not intuitively obvious. Let's put it that way. Okay? All right, we got to focus on the specific heat. The nice thing about the specific heat is that the specific heat of every solid that you're ever going to care about has almost exactly the same function of temperature. It's an S-shaped function. And when temperature is 0, the specific heat goes to 0. That's a consequence of the third law. It starts out at low temperature with proportionality to T cubed. At high temperature, it asymptotes to the high temperature value of Cv, which is 3 n K, where n is just the number of atoms and K is Boltzmann's constant. And the temperature at which that high temperature limit is reached is fixed by a material property that varies from one material to another. We'll explain why, which is called the Debye temperature. So give me any material in the whole world, and I can tell you that at very low temperature it's going to go like T cubed. I can even tell you what the coefficient is going to be. Don't worry about that. At high temperature it's going to be 3 n K, and high temperature is reached when the T reaches the Debye temperature theta D, and the Debye temperatures of materials are tabulated in handbooks. You can look at them. So the only ambiguity in what the specific heat is going to do is in this intermediate region, and it can't vary very much from solid to solid in the intermediate region, because it has to start out at T cubed and it's got to bend over to asymptote here. So for a pretty good first approximation, every material in the whole wide world, if you measure the temperature in dimensionless form as T over theta D, has exactly the same specific heat function. So life is very simple. All right, why is that? Unfortunately, that gets a little complicated. So let's talk about that for a minute. There are two possible contributions to the specific heats of solids. You heat a solid up, two things happen. One thing that happens is that the atoms vibrate. The other thing that happens is there may be some redistribution of the electrons over the available electron states. For reasons that are fairly obvious, I'll put them off till next time. The electrons make a negligible contribution to the specific heat, except in the absolute zero temperature limit. Virtually all of the specific heat is due to the lattice vibrations of a simple solid. Now, so we've got, in order to understand why the specific heat behaves as it does, we've got to understand what the lattice vibrations are doing. Remember that when you have a solid here, each atom is going to be in thermal vibration. Even at 0 degrees Kelvin, it's going to be in vibration because of the 0-point energy. It's going to vibrate in three. Its vibration can be resolved into its motion in three directions along the three Cartesian axes. In classical mechanics, you would assign an energy kT for each degree of freedom. The vibrational energy then would just be 3 nkt. So the contribution to the specific heat is just 3 nk, which is in fact the value that the specific heat has when the temperature is above the Debye temperature. However, when we get to temperatures well below the Debye temperature, we get out of the classical regime and into the quantum regime, unfortunately, and life gets a bit more complicated. To understand that low temperature behavior, to understand how the rules of quantum mechanics govern the energy vibrations, we've got to consider the cooperative motion of atoms. These atoms are not really independent, they're bonded to one another. So if I move one of these atoms, if I pluck it, all of its neighbors are going to be pushed into vibrations too because the bonds that hold them together. We need a way to describe that. We can begin to describe that in one dimension. Suppose that we have here a linear chain of atoms which are bonded together, and we pluck one of them, like a guitar string, so that we give it a transverse motion, something like this. Well, what's going to happen is precisely what happens in a guitar string. It's going to pull in its neighbor, which will pull in its neighbor, which will pull in its neighbor, and you will start a wave that will propagate down the chain of atoms. Now that wave is kind of restricted because the displacements are only defined where the atoms are. I could not tell, for example, if this were the displacement in which this atom and this atom moved is shown here, or if there was some weird high-order harmonic in which there were 4 or 5 oscillations between the two that just ended up here. The wave is only defined where the atoms are, and that places some restrictions on the number of waves. Let's assume that we have n atoms. They're separated by distance a, so the atom positions are in a, where n is an integer, 0, 1, 2, so on up to total n. And let's assume a sinusoidal displacement. U of x, that is the displacement in this perpendicular direction, is of course only defined at positions in a. We don't know what it is in between them. It's write it in the usual exponential form, u0, the exponent of ikx, or exponent of ik in a, where k is the wave number, 2 pi divided by the wavelength, lambda. Here I show the half wavelength, lambda over 2. And this is just the usual way to describe a sinusoidal wave that is only measurable at positions in a. K is the wave number. Now, in order to make this problem attractable, we do what physicists always do in solving problems of this sort. We assume periodic boundary conditions. We assume that if we have a displacement here and we go a full chain, we take this chain, which is only n atoms long, and we imagine it's connected to another chain and another chain and another chain, so they stretch to infinity. So we don't have to worry about reflections to the boundary. And we assume the properties are such that the displacement at equivalent points in the chain are the same. So the displacement at x plus na, full chain length, is the same as the displacement at x. This is what's called a periodic boundary condition. It says all these individual segments are behaving exactly the same. Well, if I take na and multiply by k, 2 pi over lambda, then this, in order for this to be true, k na would have to be equal to an integral multiple of 2 pi, so that this function will reproduce its value at each na. That says that the wave number multiplied by n multiplied by the spaceman must be 2 pi times an integer, and these are the only values that k can have. That says that the wave numbers, or if you want the wave lengths of the waves that are in here, have the values 2 pi q over na, where q varies from 1 to n effectively, or I can make them vary from minus n over 2 to n over 2, in which case the range of k turns out to be from minus pi over a to pi over a. There is a finite range of values of this k, after it will just repeat itself, and that range of values contains precisely big N individual values in the range minus pi over a to pi over a. That's what's called the first Brillouin zone of this linear chain. And that tells you that, first of all, you have discrete values of the wave number that are possible for this wave. It also tells you that the total number of independent waves that you can have is precisely equal to the number of atoms in the chain. So I've now replaced, which makes sense. I'm describing the vibrations of n atoms. N atoms, capital N atoms, only have capital N vibrations in one dimension. But I've replaced the individual ones with n waves. So I'm just replacing the description of individual vibrations with individual harmonic waves. The number of harmonic waves is equal to the number of atoms. The wave numbers are between minus pi over a and pi over a. This is shown here, the first Brillouin zone. And that describes the waves in the linear chain. Now let me go to the next thing I need to worry about, which is what are the energies of these waves? Or more directly, I'll get to the energy in a minute. What are the frequencies of these waves? How fast do the waves vibrate? I've told you what their wavelengths are, but to describe a wave, how it varies in time, I also need to know what its frequency is. Well, you can sort of qualitatively see what its frequency is going to be in the following way. Suppose I'm talking about k equals 0, or near 0, which is a very, very long wavelength. If you look at this wave and you say, what is pulling, I pluck this thing, what's pulling it back? Well, what's pulling it back, the forces, are due to the different displacements of the adjacent atoms. If this atom is displaced up more than that one, then there's going to be a pull that will try to restore that. If I took this linear chain and I displaced it rigidly up or down, there'd be no force to restore it, because there would be no pull on the bonds, no change in the length of the bonds, no effect on the chain at all. So when I get to k, if k were strictly 0, then the frequency would be 0, because there would be no restoring force against the displacement. As soon as k is not 0, there is a restoring force, and we have a frequency. But when the wavelength is very big, when k is very small, that restoring force is going to be relatively small, because the atoms are displaced only slightly, the bonds are only slightly stretched in making the wave. So if we plot omega as a function of k, we start at it symmetric, because it really doesn't matter whether the wave goes one way or the other. We start out with a frequency near 0, and it builds up as the wavelength decreases or k increases. So we get omega starting out something like this. And you can in fact show that right here at long wavelength, the frequency is ck, where c is the sound speed. Sound waves are the very long wavelength waves. And sound waves, to the speed of a sound wave in a solid, as long as it's a real sound wave, it's not really a function of wavelength. So you have a linear relation omega equals ck. But now let's take the other extreme. Suppose we're out here at the edge of the Brillouin zone, minus pi over a over pi over a. When you're out here to the edge, what actually happens is that k is such that adjacent atoms are moving in opposite directions. This one is moving up, while this one is moving down. And that's going to give you a maximum value of omega. So in the simple linear chain, the maximum of omega is going to be out here at the boundary. Since this chain has got to be periodic, it's got to come into the boundary with zero slope so that this segment can fit onto that segment. So that in a simple chain, the quote dispersion relation, omega over k looks like this. As k increases, the wavelength decreases, the frequency gets bigger, initially at the slope of sound speed, but eventually bending over to achieve a maximum here at the free wind zone boundary. And that's what the dispersion relation looks like. Don't worry about the math. It's kind of good to keep that kind of figure in your mind. The frequency goes up as k goes up, as wavelengths go down. And the reason is just the bond stretching that is associated with these waves. Well, in the real world, of course, even with a linear chain, I have got three directions in which the atoms can move. They can move transverse up, they can move transverse out looking straight at you, or they can be longitudinal, in which the atoms, instead of just being displaced perpendicular to the chain, are displaced along it. Those are the three directions. This atom can move up, it can move out, or it can move along the chain. The transverse modes in this simple model, there are two of them, up and out, are going to have the same dispersion curve because they're the same by symmetry. The longitudinal wave will have a different dispersion curve because the change in bond length at a given value k is going to be greater if the atoms are moving along the line than if they're moving perpendicular to it. So the restoring force is greater. So the longitudinal frequencies are a bit higher, and we get something that looks like this. Different modes with different frequencies. Each of these branches has precisely n values of k, so there are a total of 3n, 3 times the number of atoms, distinguishable vibrational waves of this linear chain. The next complication, and I'm going to tell you, just introduce this and then stop for today, comes about when we have more than one atom per unit cell in a linear chain. Suppose instead of having all the atoms the same, I have a big atom and a little atom, or positive ion and a negative ion, or something going along the chain. In this case, I have two different kinds of vibrations. I have vibrations in which the adjacent atoms move together. When that's the case, I just had exactly the same situation as I had before. I'm just now moving a binary molecule instead of an atom. So I will generate the so-called acoustic modes, the transverse and longitudinal modes, and these represent situations in which these two atoms in the unit cell are moving together. But it's also possible to have a whole new set of waves in which these two atoms are moving in opposite directions. These are what are called the optical modes. When the atoms are moving in opposite directions, the frequency is in fact highest right at the center, k equals 0, because you could imagine the two rows of atoms being rigidly displaced in opposite directions, giving a big restoring force. The shape of those curves looks something like this. The frequency really is not very much of a function of k at all up here, and these are called the optical modes of vibration, because as we shall see, they're very important in the optical properties of ionic crystals. Okay, let me stop there. I've just defined acoustic and optical. Next time we'll talk about vibrations in 3 dimensions and the simple little Debye model, which lets us understand what's going on with lattice vibrations without doing much in the way of fancy calculations. Okay, see you then.